to the IT group because I watched them rewire this whole room over the last hour. And I'm going to give you my take-home messages right now, so if you want to go get a beer or something like that, you've got the messages. One is we really live on an ocean planet. All the climate and weather that you experience in the middle of the country and everything is really heavily driven by the state of the ocean. The ocean holds 150 times more energy and heat than the atmosphere. And so that's the heat reservoir of the planet. And if you go through history, those that know the seas control economies, control global reach and everything, and so it's a good lesson in history. The technology we used, we were essentially blind studying oceanography, even when I was a graduate student. But the next generation, they'll be able to see the ocean. So it's a hopeful message there. And the data is going to help society. I'll give you examples from hurricanes, then I'll jump down to the Antarctic. And really, there's a mantra of a technologist we work with, Doug Webb. He's a fantastic old gentleman, and this is his theme he gave our lab, and we try to live by it as much as possible, which is work hard, have fun, and change the world. So what's the problem? Well, here's the challenge for our students going through school right now, because they're going to have to solve it over their professional lifetime. If you look at the Earth at night, that's the pictures of where lights are on continents. And we need to transform this map to look like this map. So this is the map of global population. So you see a wide disparity. So look at populations here in Africa. You know, they essentially don't have lights on at night. And so equality and distribution of energy so people can live. Population is growing, often in the areas where there is no power, and the Earth is changing. So here's the projection of water scarcity. And if you look here, areas of great unrest, that was predicted in the 70s by the climate scientists, because you were going to change farming communities into urban communities and create religious strife. And so, good luck, next generation. And the ocean is a big part of it. The problem is the ocean's complex. So all these arrows represent different processes, and there's interactions with the atmosphere, deep ocean, land. And if you look at how I was trained as a scientist, I was trained on this arrow right here. And the problem for the next generation is they need to think holistically how the whole system works. And that's actually a great science problem, and it's exciting, and they're going to have tools, but we're still learning how to do that. And the reason is can you hear me? It's rough. Sorry. This is me standing on the 3rd floor of a ship, crossing the Drake Passage. It's a nice sunny day. Most of my grad students are down in their bunks puking right now. And it's really, this is your laboratory and your workspace. And so there's some fundamental challenges in just getting work done. Here's a picture on the back deck. We're about 20 feet above the water line. Here's a wave coming in. He's buckled in, safety first. And then you have everyone else behind as he sort of gets material out to us. And you see the lines going in that direction. It's a tag line, and connected on the other end is the wheel of a train car. That's our anchor. And you can see how strong the currents are that you're carrying out vertically. And so it's just dangerous to work at sea. I was once hit by a big wave on the back deck of the ship. I managed to hold on to something, called home, and then it was a game of telephone where the message changed. By the time I came home, a rumor had spread through my town that I had died at sea. Luckily that wasn't the case, and everyone was happy to see me. So it's dangerous, and this is how we're trying to go to sea. Drive a ship around, and these are my 3 people I form a lab with. I'm the biologist, so I have the head in the water. And we drive around on research vessels, which are great tools, but it moves at the speed of about a 10-speed bike. And we stop, and we drop a bucket over the side, and we hope to describe this 3-dimensional soup that's changing every time the wind changes direction. And so early on, we decided we had to figure out a new way to do it. And just to show you, that was actually a Wisconsin cheese factory postcard. But here's a picture of me. I'm in the Antarctic ice edge. This is all ice algae ground. And it took, just like the postcard, I'm hanging over the front here trying to get a sample. And this gives you an idea of the scale you're trying to see. And so we developed a new way where we essentially beam all data onto campus, and we make it free over the web. So this is the Cool Lab. Essentially, we get models, we get data from satellites, radars, undersea robots. When we're out on ships, we do it. Numerical models, we build sensors, and we use the Northeast United States as our laboratory. So we built a network that spans 1,000 kilometers that collects data 24/7. It beams it real time back. It goes to the web. It's open access to anybody. We get about 250,000 web hits a day in the summer. 70% of the general public or companies. If you look at the domain name, it's not just nerds looking at the data. And I'll give you a flavor for some of the instruments. And when we build these systems, we have lots of interesting science questions, but we tie every science question to some societal need. Maritime safety, management of ecosystems, water quality, coastal innovation, offshore energy. This is a big one. If New Jersey has no offshore wind turbine by 2030, it'll have 5,000 because all our nuclear power plants are going offline. And the ocean data is the biggest unknown. So we build our networks not only trying to do cool science, but also help society in real time. Satellites, we all know how they work. They take these large snapshots of the surface ocean. You can measure things like temperature, storms on the ocean, you can measure the amount of plankton, and they create maps. And we build redundant networks with other universities and groups so that the system never goes down. The other one that makes surface maps, these are high-frequency radar. They're really high-frequency radio. They send out, it's a speed gun like the policemen use, but for the ocean. And we're bouncing the sound off waves of certain heights. And what it does is it allows you to make a map of the surface currents for the entire thing. Here's New Jersey, and it's going out about 150 miles. And so every hour you have a map of currents. Who cares other than a few nerds who are trying to track something? You do if you're out there and your ship goes down, or your boat goes down. So your boat's going down, you get on the radio, you give your latitude and longitude, and you jump overboard. And then the Coast Guard gets your message, and the first thing they know is the position you were at is not going to be the position you will be at when they get out there, because it takes time to muster, and it usually takes hours. There used to be so much uncertainty that if you called in this point, the uncertainty of your position was almost the size of the state of New Jersey. We reduced the search area by 70%. And 70% searching reduction means more people will live, simply because the longer you're in the water, the more likely it's going to die. This is now the most requested data source by the Coast Guard, and it's only a few years old. Well, I know this is Salt Lake City, can't help you there, but if you look at the country as a whole, the Coast Guard is incredibly good at rescuing people. They rescue about 10 people a day on average in the United States. The problem is 13 people go in the water every day across the United States. There's going to be a national network built around the country with this because of that. We think we will rescue 2 of those 3. Third, shark. And so you get surface maps. Drones are moving in. So here's a nice fixed-wing drone, and this is a map of penguin rookeries. And these little drones now can make high-resolution maps down to centimeters. And we've been mapping penguins on this island for almost 20 years. It took 6 days. We drop off 2 graduate students, we drive the ship away, we let them live in tents, and they count everything, we go pick them up when we're done. This drone here, this small guy, can map everything in about 40 minutes. And if you look, you see all the orange, that's penguin guano. You see little glowing things on that one, those are adults and chicks. The chicks release more heat, you can tell the difference. You can also do ecology. These are humpback whales, and they form bubble nets to get all the krill concentrated, and they come up right through the middle of it, swallow all the krill. So here's one. You can see another one coming up here with his mouth open. And you couldn't sample this before, because the way to sample it is you go out in a Zodiac and you sit in the middle of the public market. That's not a good place to be. So the drones are allowing us to look at behavior. Here we've actually radio tagged with a video camera a whale. It's swimming around, we're getting pitch and roll. You're going to see it open its mouth as it swallows. It's coming up in a minute. And then you'll see the krill that got away sort of flowing by its body. So it'll start looking out. There's the big gullet opening. And then you start seeing the krill that, are very happy they escaped. So now we can actually sample animals underwater. That's cool for biology. It's incredibly important for the physics. So the Southern Ocean, the largest ocean that drives climate on this planet, we don't even have a heat budget right for it. That heat budget was solved by radio tagging elephant seals. They collected so much data swimming around looking for food, we finally had the data. The seals solved what the humans couldn't do in 2 years after a century of work. Let's talk about the robots, because I love these guys. This gives you an idea of scale, 150 pounds in air, neutral in the water, and it's a buoyancy glider. So here's a swarm of them, and essentially they allow you to maintain almost a continuous presence in the ocean, but you're connected to it every time it surfaces. It comes up and checks on how things are going. And so if you look at what our lab has been doing, so we're just a lab, and all these red dots and red lines are missions we've flown off on campus. And the great about being on campus, it means undergraduates get to be part of it as it's happening, as opposed to reading about it in a book. Science is fun if you're doing it. Even I will admit, science reading it out of a book can sometimes not be exciting. So you can, as a group, have a global presence, but now there's no reason any undergraduate in the country can't access the data and be part of the experiment, because it's all over the web. And that's been enabled by the Global Communication Network, Iridium. So, and I apologize to students who heard this story earlier today, but when I was just about to start graduate school, I was down in Antarctica at Palmer Station, and this is how we called home on the ham radio. One-way communication, and then you say over, and then they talk back, you say over, and the whole world gets to listen to the conversation. Given a lot of us broke up with our girlfriends and boyfriends, it's pretty miserable. It was the way we did it. Now if you compare it to Iridium, so you see the robot here's got its tail above the water, that tail is the global phone, and that calls the lab in New Jersey. And we were out doing an experiment, we were on a ship out here, the British were up here in the base, and it was all controlled by our lab in New Jersey. That's our old lab before we cleaned it up. It was really controlled by this guy, Dave, and he was coordinating the pickup. So the red line is what the robot flew, the blue line is what we wanted it to fly, having to go through ice fields and all this kind of stuff. And he had a date in New York City about when it was supposed to be picked up. He took his smartphone, he got in the car, he moved the pickup time by a half hour, had the robot fly into the Brits. He wanted to do it because he wanted to get the robot picked up before he hit Lincoln Tunnel, in case he didn't have a cell phone connection, smartphone connection. So this guy controlled a robot in Antarctica while driving on the turnpike and still had dinner, in the city. And so that is unprecedented. That was science fiction, even when I started as a young professor. And the new generation can be anywhere on the planet at any time, all the time. We're still learning how to do experiments and do the science with that kind of approach. How do these robots work? They have a little ballast pump in their nose. They suck in water, about a coffee cup. They have batteries right here. They pitch those batteries forward to get the nose to dip down. So it's just like the submarine movies in World War II, everyone run to the front. It sinks forward. It's got wings to sort of get it in the forward direction. Gets to the depth it wants. It pushes the water out. It pulls the battery back, and now it starts floating up. So it's doing a sawtooth through the water. In the middle, it's carrying science sensors that are just recording data continuously. And then every so often, it comes up to the surface. It calls home. First thing it does is checks its position. Am I lost? Am I off course? Then it checks, is there a human who wants to talk to me? Then it checks, did the human leave me an email because the human's lazy? And then it goes back on its way. And by getting rid of the propeller, you now have a robot that would last for a day at sea, and now it can last for a year at sea. So you can cross big distances, and you can do it from the comfort of your home. And because you're collecting so much data, you get sheets of data. When you go out on the ship, you get a profile, 20 miles later, a profile, 20 miles later, a profile. So we can see things we couldn't see before. And the global omnipresence, a good example, is a glider Darwin. We were flying with our friends in Australia and Perth. So here we are, we deploy the glider in, it's 3 p.m. their time, 3 a.m. our time, we get going, we go home, go to sleep. While we're asleep, it happens to surface right by the guy who's sport fishing. His reaction, of course, I'm going to steal it. But unfortunately for him, once that robot is in the air, that tail can talk to us. So when we came in the next morning, right there, he was parked somewhere in one of these berths. He put the robot in his truck. He took Highway 34 outside of Perth. He lives in that house. He put it in his front yard, like a little gnome. And so we decided to mess with him. We have a sensor on there called an altimeter. It's a chirping sound. We turn it on. It attracts the attention of this neighbor here. He looks over. You see it's got wings, it's yellow, it has a big American flag on it for flying things, and this was during a Gulf War. And so her natural reaction is, oh my God, you stole a cruise missile. She threatened to call the police. He panics. He throws it back in his truck. He drives back into Perth from Highway 34, dumps it in the grove of trees in the warehouse district. We're watching the whole thing. At this point, we got popcorn. All our Aussie friends in, they dust it off, and they throw it back in the water and does this experiment. We did send a letter to the guy. The first one, we pretended to be the CIA. Don't ever touch us again. And then a week later, we said, no, we're from a university, and we sent him some swag. So, you can be anywhere, and you can see things in real time that you couldn't before. So now let's take 2 examples of how this data is going to help society. We're going to start with hurricanes because that's where we spend a lot of time. And these are all the hurricane tracks. So they start off Africa, they strengthen, and then they swing in depending on their trajectories. And the thing about hurricanes and cyclones, if you look at the billion-dollar events that affect the U.S., look at the amount that's associated with these large storms. And so these are the most destructive storms where you really measure the damage in billions of dollars on every event. And we see it every summer. We had Hurricane Michael before, we had Houston before that, and before that was the Northeast. I was just in San Juan, Puerto Rico last week, and that island isn't even close to recovery. Essentially their water system is failing for half the island. And so these are incredibly destructive events. The good thing is we make progress, at least in Western society, to deal with the storms. We measure it in billions of damage. If you go to mega typhoons, which you see in Asia, we still measure that damage in terms of how many thousands of people die. And that's something we have gotten better. If you combine all the other natural disasters, hurricanes equal that for the U.S. over the last 10 years. So it's a big problem. So the Weather Service has been working really hard on it with public investment, and they've really improved forecasting where the hurricane's going to land. And it's amazing the technology they built to do that. When Katrina hit New Orleans, it went around the city and came in from the backside, and they predicted that. That's amazing. That was a pipe dream before. The problem is if you look at us predicting the intensity of the storm at landfall, it's only shown minimal progress. So here we've increased the prediction by orders of magnitude, and here 10%. And you could argue it's not even significant because of these good things. So we don't do intensity at all. Why does that matter? When a storm is coming, you need to decide, do you evacuate? Do you stay in place? Where do you reposition power trucks to be there immediately after the response, along with first responders? And the example from Sandy was they had all the trucks pre-placed. There was so much error in the surge, they parked the entire power rescue fleet 1 mile too close to the beach. And it was wiped out. It was $100 million worth of damage to the rescue fleet coming in. So we got to experience them live in real time. First, 1 year we had Hurricane Irene. This storm was reported 15 billion damage. It had been the first one along the upper Northeast in a long time. The intensity was way over predicted. At the time, we had a very quiet Governor Christie, you know, and he was on the beach beforehand screaming, "Get the hell off the beach," in classic New Jersey style. The storm veered a little bit, and it turned into a massive rainfall, and we evacuated 1 million people from the New Jersey shore into the flooding area. So that wasn't too hot. You know. A year later, Sandy came. Much worse. We under-predicted the surge. That's where the power trucks. And what happened on the Jersey shore is no one believed the forecast from the summer before. So there was a huge amount of rescue of people trapped down at the shore because they didn't believe the forecasts. The one thing you need to know about the mid-Atlantic, here's the ocean, here's shore, here we're going offshore. In the summertime we have hurricanes, we have a super hot surface layer of ocean, and we have a super cold remnant cold pool, we call it. It's essentially, it's a 1,000-kilometer undersea river that runs along our coast, and that's going to come back and tell you about the hurricane. We call this barrier a thermocline, and that's the strongest ocean thermocline on the planet on a hot Jersey summer. So you go from 28 degrees to 8 degrees in 1 week. So let's look at Irene. So here we are looking at sea surface temperature. Red is hot water, blue is cold water. This is before the storm hit, right here. This is what it looked like after the storm. It was an 11-degree difference. What happened? Well, as the storm was approaching, we happened to have a glider out flying off New Jersey, off the coast, one of those robots. It was actually flying for the state measuring water quality, because a robot can collect way more data than the traditional way they did it. And before the storm arrived, essentially the storm was strong enough to cool the ocean by 5 degrees in a half hour. So it makes the ocean, instead of a fuel source to the storm, it becomes a fuel sink. And that's why the intensity was over-predicted. And it was because of that cold pool that existed. And it had some currents circulating that sort of pushed the water on, the hot water onshore, but because it was 2 layers, it set up a reverse flow, and you transported water offshore underneath, and you didn't have as big a surge. The Weather Service couldn't see that, because the Weather Service only uses satellites for their ocean data, and once clouds come, there is no more data. You can't see the ocean surface. So they have to assume the ocean's constant, but it wasn't, it changed. So this was the forecast they did. If you run the forecast, if you put the real ocean in, this is what the storm really looks like. And the difference in terms of the storm is a Cat 1 hurricane versus just a tropical storm. It's about, 15 knot reduction, 50 mile per hour, 20 mile per hour reduction in wind speed. So we have the smoking gun of why we don't do intensity. We don't have a real ocean in the Weather Service models. The Weather Service acknowledged this. So this is Lou Salini, he's head of the Weather Service. A week after Sandy, he actually came up. This is our ocean data class. And he challenged the undergraduates. His message was, you can't wait for you guys to be PhDs to solve the problem. People are dying now. And challenged to use the data and figure out why our models were so bad. And this is a paper that was published, and those are undergraduate first authors. So my message to undergraduates is not to wait to graduate school to be a scientist. We need you to be a scientist now. Okay, so that was one wants a sidle benefit, let's go to a picturesque place that's also showing the Antarctic. I work on the West Antarctic Peninsula here. Blues mean that ice is growing. Red means ice is melting. And this particular place on Earth is the fastest ice melting place on the planet. And it affects what lives there because the entire ecosystem essentially is structured around the sea ice, presence or absence. So let's show you some of the temperatures. So here we are in the 50s. This is winter air temperature. And we've gone up almost 7 to 8 degrees average winter temperature. Is that a big deal? Well, think of it like your freezer. You got your ice cream in there, it's below 0, it's great. You dial it up 4 degrees and you're near 0 or 1, it's not as good. It's mushy. And the other thing you see is these big oscillations. That's what you expect in polar systems, but that's disappeared. It's become a maritime climate along the West Antarctic Peninsula. This is sea ice, so in 2 locations, and showing you it oscillates year to year. But generally, it's been declining. This last year, we were back down here. So the place is warming. Ice is melting. 87% of the glaciers are in full retreat. And things are happening now even on land. Soil's being made naturally because it's not covered with ice. You're starting to have plants. And by the time I retire, there will be rooted plants growing on this place. We got involved for this long-term project. We just finished our 27th year down there 2 weeks ago. I took this year off. But essentially what we started with was looking at penguins. And so this is the Adelie penguin. There's 2 types of polar Antarctic penguins. There's happy feet, the big emperor one, about up to here, and the Adelies are about up to 20. And they're awesome. And when you look on the West Antarctic Peninsula, their rookeries aren't uniformly distributed. They're in very specific locations, and we wanted to know why. And this is Bill Fraser, who essentially has been following the penguins since the 70s. He got out of Vietnam and decided he was going to become a penguin biologist, and has pretty much lived on the ice this whole time. And he's been tracking the population, and it's not looking so good. So here's the Adelie at Palmer Station, and there used to be almost 16,000 breeding pairs. We're down to about 1,000. And so he's tracked that. And islands he used to go to that were so loud with penguins now are empty and barren. And all he hears is the wind. It doesn't mean that life disappears, life changes. So these penguin species, kinstraps, gentoos, they're subpolar. They live to the north, and now they're invading in the Antarctic. And so you're seeing a whole new community move in. And so we wanted to know what was driving the changes and why were the penguin rookeries not equally distributed. So what's driving the change? It's the deep ocean. Here's Antarctica, and this is the Antarctic circumpolar current. It's the only circumpolar current that's unimpeded by land on the planet. It's the largest current on the planet, and it's flowing at about the speed of 75 Niagara Falls continuously. It's deep. It's about 300 meters, so just about 1,000 feet under the surface. You can't see it from the satellite. And it's warm, 4 degrees Celsius, balmy for down there. And what we're seeing is the areas that are melting is where this current gets really close to the continent. So we think that it's spilling heat over, and that's what causing ice melt. Areas that are still growing ice, this current essentially veers way offshore and comes back in. So this area is losing ice, this area is losing ice. So how do you sample it? So the current comes along the continent, there's a continental shelf, and essentially the current interacts with the edge of the shelf, and a little piece breaks off every so often and goes onto it at 300 meters. We have to use robots. And so those are the gliders. They can be out there all the time. They can be at 300 meters. So these are the maps we've made of these squirts of hot water coming in. And then we surf them underwater at 300 meters remotely from New Jersey. So essentially we look for a temperature fingerprint of the water, and then we try to follow that temperature for as long as we can. So we do it for about 7 days. And as these eddies essentially get carried close to shore, they lose heat. And that's the heat that's warming the atmosphere. Because the ocean and water pull so much more heat than air does that it is capable of carrying a great deal of heat out. And so it's little squirts of deep ocean water that's melting in this place. It's not the atmosphere. Okay? And it's associated with these large canyons that were carved by ancient glaciers. And they come in and they flow in, and they happen to end up at all the major penguin ranges. So in the past, this was a completely ice-covered place. The penguins still needed access to the ocean in wintertime. And here, these warm blobs would be carried in by the undersea canyons and then upwell heat and create what we call plinies, which are areas of open water in wintertime. So they formed, these guys picked their colonies based on sort of conditions of the past. And now it's all changed because there's no longer ice up there. And so if that's the case, you should be at the penguin colonies be able to see warm water coming up and surfacing into the colonies. So here's a glider map of it. There it's upwelling hot water. That's opening up the Glinia. Here's another one, penguin colony on this side of the island where the hot water is. Not really on that side. So if you want to measure change in the ocean, you've got to connect all these linkages from the deep ocean, small scales, all the way to the end. That's really hard. We couldn't do it before, but now we can. And so we can do stuff. So how are the penguins being impacted? Only 2 more science slides, I promise. So this is called an anomaly plot. So if you're above 0, it's a big year. If it's below 0, it's a low year. And this is the amount of plant material in the ocean. So some years you have not much plant material, some years you have big. This here is a map of what the penguins are eating. And they eat krill, Antarctic krill. And the krill are in lots of sizes. So when they're small, they're baby krill. When they're big, they're adult krill. We didn't kill the penguins to get this data. You essentially catch the penguin, you pour a little seawater down its throat, it pukes, and then the scientists gather up the puke and shit. So very romantic. So what you see is in a year where you have a big chlorophyll peak, it's an adult population of krill. Well, they got a lot of food, they kind of have a party, they open a glass of wine. The net result is a huge amount of recruitment of larvae the next year, and you reset the population. Here it happens again, reset, reset, reset. So it's a tightly coupled food web. If you change the amount of plant material, it directly affects the krill sizes, and then that ripples up to the penguins. So as it's melting, what's happening to the plants? This is comparing the 70s and 80s from satellites of the amount of plant material in the water. So in the south, it's red, there's more plants. Blue means much less plants. Why is this red? This used to be completely covered with ice. So it's a tabletop. There wasn't much sun getting in the ocean, and without sun, plants can't grow. Here, well, it's completely ice-free. Now it's feeling the full force of the Antarctic wind, and the ocean's mixing really deep. So the plants actually are getting much less light. And on top of it, this atmosphere has become moist. So it's become cloudy. It used to be open, dry, polar atmosphere. Now it's cloudy. So this ocean has become darker. So as you turn down the light, you turn down the amount of plant growth, and that's where the penguins are declining. And down south, you've removed a tabletop, added light to the ocean, and the ocean is turned on. Once the ice is fully melted here, it'll transition to blue. Okay, so we have cool toys, we can go to cool places, now we got to educate the next generation. So here I am trying to inspire a series of Asian kids giving a lecture in Taiwan. At the same time, we need good teachers. I found this on the Whisper website, where people put up their thoughts, and I'll just read what people perceive as science. I don't want to be I want to be a math and science teacher, but no one wants to marry a boring person like that. I don't want to die alone. I agree with that, you know. And so we do a real bad job of communicating science. And, you know, there's lots of great tools to convey the excitement of what we do. But I know I wasn't trained in that, and I'm still learning. I was at a storytelling conference the second week of January, just learning skills. At the same time, the government was really concerned we're not training the next generation of scientists and engineers. The amount of students going into those degrees is going down. And they're tending to be more conservative rather than during the space race, let's go change history, let's do something risky. They're becoming much more risk averse. So we were in a meeting, Dr. Rick Spinrad, former administrator for NOAA, said, I'm taking you guys out for a drink. This was his first sentence. You know, I had something you can do for the good of the country. You're like, oh my God, this is a conversation. And he told us to take one of your gliders, modify it, fly it across the Atlantic. No robot had ever crossed an ocean basin before, and have your students fly it. And then he left us. And his driving concern was this National Academy work, Rising Above the Gathering Storm. It was Bill Gates Sr. and a bunch of industries and corporations that commissioned it. And their concern was, how do we get more scientists and engineers? So here was the challenge. At the time, that green line was the longest mission we had ever done. The red line is what our boss told us to do. And the power budget for the gliders is 3 of those Christmas tree lights per day. And so how do we expand the mission to get all the way across an ocean? And so it was risky. It was something no science agency was funded because they become risk averse. But luckily we had a donor who happened to call and we said, we want to do this. And he sent us a check and said, go do it. We built a glider. It immediately caught on across the whole university. Here's his Facebook friend. It was single at the time. 185 friends. I had about 80 friends at the time. And we sent it across the ocean. It got all the way to the Azores, and it was eaten by a shark. After the students had lived with it for about 150 days. We know it was hit by a shark because we couldn't go get it. It was about 90 feet under the water. It was going up. Something very big came up, struck it from below. That's a typical predatory shark thing. They swim circles underneath you and then move in. They bite, they try to wound its prey, and then wait for it to die before they eat it. The glider has some behavior. It's in panic mode. It starts to leak. It panicked. It jettisoned it, waited, it got to the surface, but it was so far out to sea there was no way we could get it. So we toasted it with coffee, downloaded the engineering data so we could see what happened. And it drowned. And then we went back to the undergraduates and said, this is science. You're going to take risks, you're going to lose stuff. We rebuilt the glider, and then essentially the second attempt got all the way to Spain. We went to the town of Bayona. It was the student's choice, because that was where Columbus's ship, the Pinto, was the first to return back from the New World. The students who were helping fly it started as a group of 2, and by the time we finished, we had a group of almost 70 per term, and 30% were non-science majors. We had art majors, English majors, and they were realizing data wasn't fun. We turned it into a community event. New Jersey kids filled the glider with letters to Spanish kids. The Spanish kids picked them up, returned it, it became an international event, recognized by Smithsonian. But if you look what it does for education, here's enrollment in marine science majors. So this is prior. Here's our 4-year cycle of this whole mission. We almost doubled enrollments. We increased diversity by a factor of 2, and that hasn't dropped off. Then when you're an undergraduate, you can do informal research. That's what a lot of our students were doing, or you can do formal theses. And that can play out. If you're doing informal research, you can do a formal thesis. It's good. And so it had direct impact on the community. So in conclusion, and looking forward to the next generation, because they're the ones who are going to carry the torch to the finish line, you're going to have great ways to see the ocean that was, something out of movies when I was coming out. Being able to see the ocean, manage it, use it in a sustainable way is going to change how humanity lives with the ocean. And we need it for energy, we need it for food, we need it for all kinds of resources we don't have on land. It's most of the planet. And the great thing is anybody can be an astronomer. So even though you're not living right at beachfront property yet, you're going to be able to be an active part of it. And so I really thank you for your time coming out and listening to a geeky lecture on a Tuesday night, but it's my honor to be here. So thank you. So this just gives you an idea of what the West Antarctic Peninsula looks like. That's in Delhi. They're amazing in the water. That's a teenage one losing its down. That's a gentoo. Here are elephant seals, albatross with its chicks. You sort of get an idea of the scale of ice skates right on the ocean, mountains, and then glacier calving is constant around there. It sounds like continuous thunder. And this was just cool. So, anyway, thank you again.
Great. Can you hear me? Is this on? No. As well?
My turn?
Thank you. Great. So I really want to open this up for questions, but I want to start with some questions that some Westminster students put together this morning. So I'll ask one to get started, and then I'll take some other questions. One thing, and given the nature of this group, one thing that was really of interest is that working in Antarctica, much like working on the space station, is an international effort. And their question is, of the researchers that you work with in Antarctica, how many different national cultures are represented, and what are the benefits and challenges of having an international team?
So the Antarctic is actually a science preserve. It's the only place on the planet where it can't be mined. No one has, a claim to the land. If you go to Chile and Argentina, they will claim to own the peninsula, and they will fly down pregnant women to give birth on the ice so they can claim to have native Antarcticans. No one recognizes that. So pretty much all countries have...
I'm just stuck at pregnancy tourism.
They got the citizenship. And so what's really nice about that is you have a distributed network around the whole continent, because all the countries have it, and we actually collaborate very quickly. So when I launch a robot from the US base, now I often fly it down to the British base. They pick it up, they rebattery it, and they fly it home to me. So we can cover things when the ships aren't there. Because a single ship day costs $75,000 per day before you pay for the science. And so it's very limited ship time. So the robots, they cost about $30 a day to fly. And if you want to buy one tomorrow, Visa card, you need a $150K limit. But you can buy it. And so if you think about it, it's only 2 ship days to have a robot that can be flying there 8 months of the year on average. And so it really changes what you can do. But you need the partners to do it well.
Great. And some people might not realize this, but when I go to a science conference in a different country, the language of science is English. And I feel really humbled by that. Is that true when you're doing science in Antarctica?
Yeah, the science language is English, which is great because I can speak broken Swedish and that's about it. And so the communication is good. The stations all call each other at regular times to give weather updates because the weather forecasts down there are really poor. And the problem is when you're working at a land base, you essentially sample the ocean from zodiac. And so if you're working 5 miles away from the base and a storm comes over the glacier, you have about a 30-minute window to get back. And it'll go from 0 knot wind to 45-mile knot wind within 30, 40 minutes. And so there's a lot of cross-communication. There's also a lot of cross-cultural experience. We play radio darts over the radio with the British.
Is that kind of
on
like
Saturday night.
Battleship? Or?
Yeah, so you have to trust each other. They're always beat us in the early part of the evening because they're British and they're good at it, but then they drink faster than we do. So by the end, you hear lots of howls and this and that. It's starting to
Yeah, but if you were to plot like number of drinks over time and darts, there's kind of a peak about midway, and then there's a drop, steep drop. Yeah.
So there's, that's why many of the Antarctic researchers are so scarred.
I see. Makes perfect sense. Questions from the audience? Yes.
So there have been some recent articles about desalination and depositing of brine back into the water.
To create fresh water.
Create fresh water.
So we're asking about desalination.
Right, and so it seemed to me that desalination was the answer. Apparently not. What do you see happening with that? Is there, if you dump it far enough out in the water, does the fresh water coming in from ice melting and stuff, does it kind of zero out?
The big problem with the ice melt, so if we think about ice melt, sea ice grows and melts every year. And the Antarctic grows more sea ice in a single winter than the entire land area of the continental United States. When that sea ice freezes and melts, it doesn't change sea level. It's ocean just changing phase. The Antarctic continent holds something like 95% of the planet's fresh water, frozen in ice. So the ice caps in certain areas are, we're talking hundreds of kilometers thick. And it's the glacial part that is what we're adding that's the issue. And the problem is in certain areas, that warm ocean water I was talking about gets underneath and trapped under the ice shelf. And that's what's causing these runaway ice sheet collapses. The problem from the science side is I can tell you the Amundsen Sea ice shelf is going to collapse. And it's going to raise sea level by 6 inches, which means my little beach condo is toast. So the storm will take it out. But I can't tell you whether it's 20 years, 100 years, 275 years. That's an open science question, but we know it's going to happen. The reason is there have only been 2 data sets collected on our ice sheet, both by robots, just within the last 5 years. First robot died within 15 minutes going under it. It cost the British government something like $30 million. The second robot made it in and out, did a 4-day mission, but that's all the data we have to work with. And so it's really the state of the ice that's on the continent that's going to affect us. The top ice shelf on East Antarctica is super thick. It'll be, even the students will be gone from this planet by the time that melts. But when it melts, if it melts, that's an open question. You're talking almost 30 feet of sea level rise. And most of the world's megacities will be underwater. So there's lots of geoengineering ideas. And I haven't heard much about the desalinization other than trying to alleviate the fresh water stuff. The problem is if we shut down CO2 today, the ocean is already, deep ocean has already absorbed 0.02 degrees Celsius of heat. But that is so much heat that the planet will continue to warm for at least 150 years. So I'm an optimist. We're going to have to be resilient. We're going to have to think smart. We're going to have to design differently. And that's the challenge that might affect me if it's a hurricane, but it will definitely affect the next 2 or 3 generations.
Okay, so there's one over here. Yes.
Are you able to...
Sorry, is there a microphone? You want to take the microphone over here? Thank you. Everybody can hear a little better.
First of all,
I can repeat the question.
Testing.
Yeah, there you go.
Testing. Okay, there we go. First of all, thank you for your Your speech was excellent. My question is with these drones, are you able to detect pollution, and to what level?
Yeah, so what we do now for New Jersey is, the big concern off the New Jersey coast, which is, example is low oxygen. If there's too much pollution in the water, bacteria go crazy, they die, they fall, it makes low oxygen bottom water, and it'll kill all the shellfish. And that's a big deal in New Jersey. The scallop fishery off Jersey is the most profitable in the country. There have been big events in the past. And the way they would sample is they'd go out in a boat, they could afford to do 13 days over the entire summer, and they could collect about 30 data points in the summer. We can continuously collect oxygen from the glider, so we essentially patrol the entire coastline of Jersey now for the state, collecting oxygen data. They can see if there's an area that looks like trouble and send the robot back and map. Is there a plume of low oxygen? Is it just a unique event? We can now measure ocean pH. There's a big concern of this in sort of coral reef areas. And so what's really nice now is the robots are mature. And so the big race now in engineering schools is building the sensors. We're going to be able to measure plastics in about a year and a half. It takes about, from you having a cool sensor, the toy, it takes about 2.5 years to get it integrated and flying. So right now, there's a lot of grants going out of universities and engineering departments, not to build whole robots, but all the sensors. And pollution is one of the highest priority ones that will happen. And the same could be done in inland lakes. Inland lakes are a great area for these kinds of technologies. These are small. They can be out there for months at a time and essentially map them. They're in the Great Lakes right now.
Okay, someone else back there. Yes.
Hello. Dr. Schofield, I really liked your pictures. I like that video at the end especially. But my question is, what powers the battery to help your robot under the water for 1 year? Maybe I can use it in my car.
Yeah, well, actually, it's the same race you got with the cars. So we started with alkaline batteries, and it was literally, we'd sit at the bench and we'd solder together 60 D-cell batteries together into a pack. The lithiums have now come on. So just like your computer's got lithiums, high, long duration, it's just our lithium pack isn't just a little square. It's like a cannonball of lithium. But there's a new technology we're going to test next year. The ocean has a warm surface, colder deep water, and we're building what we call a thermal glider. It's got long tubes on its belly, and when it's in warm water, the material in the tubes is liquid, and when it sinks down and it gets to the cold water, it becomes solid. And that allows us to push ballast oil around and essentially now think we can extend the life up to 3 years based on using the ocean's energy based on the temperature differential. It's like a delayed battery. Yeah. But the lithium batteries have made a remarkable change. We're going to transition. We use experimental lithium batteries for the long missions. They're expensive. They cost $16,000 a pop. Yeah. But you're going to see for almost a year. If we're doing coastal missions, we switch to the alkaline because they're more environmentally friendly. But now we're getting rechargeable lithiums. So if we're mapping pollution, we don't have to take the glider apart, put new batteries in. You pick it up, you clean it off, you plug it back in, recharge it for a day, put it out the next day. So we lock rechargeable lithiums, and lithium is what we call
Awesome. Who else? Other hands? I have another student question. Jeremy, do you have one? You look like your hand's almost up. Yeah, go for it. Can you pass a microphone to the middle? Or Jeremy, can you just speak loudly? We'll get it to you.
So we were just discussing the lifespan potential of the gliders, and that kind of led me on a train of thought, potentially
so there's been lots of ideas like that. Solar doesn't work well because you need to have such a big flat panel. It changes the whole engineering of how it flies, and these are supposed to be very efficient to maximize its lifetime. They move slow. They're only floating and sinking, so they can go about 20 miles a day because you can be out there for so long, you can make the distance. The other problem with being at the surface is you're just floating. And so you're drifting, you're not, you're drifting on course. And two, that's where you get damaged. Waves, ships, sharks. We've had 4 gliders stolen by ships. I told you the Australia story. The other one was off Puerto Rico. A guy claimed salvage, that if you find something floating, disabled, you can claim it. The problem for him is we knew where he was, and we were there by invitation of the Justice Department of Puerto Rico. So they sent a jeep over to the guy's house. So we really try to minimize being at the surface, because that's where damage always happens. We've lost 9 gliders since we've been flying since 1997, so that's kind of sucky. It's like we've lost $1 million. But we've been at sea almost 13,000 days, and that we couldn't have done before. The other idea we've had is sort of go down, maybe about 100 meters in the deep ocean. There's an layer where there's a lot of waves. So what you often don't know is there are these giant undersea waves, often hundreds of feet tall, generating energy. So we thought we could have one of those shakers that essentially wind it up. And so park it in the wave area, wind it up, go on its way, wind it up. The problem is that place also attracts a lot of animals. So in November, we had a glider off Sri Lanka flying in the Indian Ocean. It was attacked by something at 300 meters under the surface, right in the wave zone. It was held there for 3 hours. It was a giant squid that attacked it. A few of us got there in time. We picked it up. And you could see the beak marks of the giant squid, and its foot actually gouges through the lead hull. And the way the squid eat prey is they'll grab it, and they eat it like corn on the cob. So they eat and circle around and eat meat. So you see a fish eat one, it's a head, it's a spine, and a tail that's been eaten by a squid. And this had all these gouges circling the body, and their suckers are acidic. So wherever the sucker was attached, all the paint dissolved. And so part of it is you're dealing with how do you minimize your exposure to issues, but at the same time maximizing power. We've looked at wind too, but it doesn't seem to be it. So wave energy is part of the best bet. But the other problem is you start growing things. And like we're balancing this thing to a coffee cup in terms of ballast. So if you grow too many barnacles, you can't fly well because the technician's looking at how straight you're flying every time it calls in. Sometimes the barnacle's open on this side, and it becomes a sea anchor, and it pulls the glider in this direction. The technician gets busy, reprograms the whole thing. Next time it goes down, they open on this side, and it gets pulled in this direction. One big problem we've had, especially in the Gulf of Mexico, are those remoras, those fish that suck on the belly of the shark. I hate those things because they're about a foot long, so really heavy. They latch onto the belly of the glider. The glider immediately sinks to the bottom, and after 48 hours, it'll blow its weight and we have to go to bed. The only thing we seem to have luck protecting the glider from the remoras, and I don't know why, is women's pantyhose. We tried everything, and so it turns out pantyhose is the best protection against the remora. For some reason, great graduate thesis.
That's awesome. Several of the students' questions centered on making this issue of oceans local. And it's been a long time since we had an ocean in Utah. So I will ask you, what can we do in Utah to help with the situation with respect to the oceans?
Well, I think the big change is like before you had to go to an ocean school if you want to be an oceanographer, right? And the only people who were oceanographers were those 30 people who went on the ship. You know, and if you go into a grade school and you ask them to draw an oceanographer or a scientist, they draw a bald man with a beard, with glasses and a lab coat. And that profile has changed. So right now, it's all about remote access. And you can be an atmospheric scientist today. The resources exist online for free. You have to find them, and you have to do a better job getting it to people, give them tools to visualize it. You can go be part of all our experiments today, you know, through the online process. That's one thing that's changed. Before you had to be local to do that. The other reason is why should you care? There's lots of local issues, regional issues. Why not focus on that? Well, you are interested in things like, why is your weather changing? So the jet stream that affects all our planet and country has become much wavier over the last decade, which is why we get longer periods of heat and longer periods of cold. You know, and so, and that is a direct interaction between land, inland land, where the atmosphere is heating, you guys, and us, the ocean heat. And so my goal is I want classes around the country to join up and essentially solve them together using the data. And so I want to have classes where my undergraduates in New Jersey are working with Utah undergraduates from Spain, undergraduates from Africa, and essentially work together. And I just don't want scientists, I want artists, and I want English majors, because scientists really are not good communicators. You know, my first draft of the lecture was all in differential equations. I decided to change that. But I think that getting those communities working together is actually critical, because we don't do a good job. You know, I grew up with Jacques Cousteau. I couldn't wait to be a scientist. You know, during the challenge to go to the moon, that fueled that whole generation of scientists and engineers. What's our grand challenge? Well, I would argue for the next generation, you better tell us where the planet's going. You better design society to be resilient. And you can get rich, and you can be famous, and you can get all the benefits of that, but you're going to have to do it together, because it's a bigger problem than any of us can solve on our own, at a university, at a country. And you guys have the tools to do it, you got to do it now.
That's very good, very insightful. We often talk about with the Utah watershed how the watershed doesn't stop at the state boundary, and how you have to deal with different municipalities with respect to states. So you've just taken us to thinking about that globally, which is a much bigger problem. Yeah. Yes, back there, and then oh no, you've got the microphone. You go ahead.
Okay, thank you.
Thank you.
I kind of intercepted the microphone as it was coming by. But anyway, I have two questions. First one's kind of dumb. You always refer to it as flying. Why do you use the word flying instead of swimming when it's underwater? And then the second question is, when it's underwater, how does it communicate and know where to go?
Yeah, so I call it gliding just because the way I think of it is there's these big currents in the ocean. So just like in the atmosphere, you get these depressions and highs that lead to atmosphere, we have the same in the ocean. And what we try to do is to get on the right side of the storm, to have the storm slingshots, because the storms are rotating much faster than the glider. So the better word I should use is surfing. You know, but being a Southern California boy and still some blonde hair, no one takes me seriously. Dude, yeah, and so it's just a bad habit. You know, so, but essentially we're surfing undersea currents as much as possible to maximize our speed to get somewhere. And then what was your second question? I'm sorry. Oh, so underwater it's blind. So when it comes to the surface, we'll say, go to this point, and that point is about a distance that's about 2 to 3 days away. And over the time, when the glider comes up to the surface, it'll say, okay, where's my GPS? Okay, the currents have carried me off course by 2 kilometers. I'm going to rechart a new mission heading to that point. And then back on land, what we're doing is we're looking at all the ocean forecast models and predicting when it gets to that point, where should it go next 2 days from now. So you're updating it constantly on every cycle. But it is scary, right? It is a lot of money. put a lot of sensors on it, it's a lot of money. And when it's underwater, you're just hoping, it's kind of like your teenager, you give them the keys to the car, and you hope they make it home. And so it's experience with that. But, you know, the value you see is unprecedented. But occasionally the glider will disappear. We had one that got trapped under, we think, a coral reef ledge, and stayed underwater for 3 months. And we were just about to claim it dead, and it showed up that day. And then some just disappeared. You don't know what happened. So we had 2 deaths of glider. They were like my kids. That's why. Live and die, fly. And we don't know why. We think one was a leopard seal. Leopard seals, they don't have sharks in Antarctica. They have leopard seals. They're about 15 feet long. Their head is about the size of a horse, but they have jaws like an alligator, and they are mean. And they will attack zodiacs. They come in and sharpen their teeth on the boats and the dogs, and they'll just attack and kill people. They won't eat them. They just kill. And so there are some aggressive animals we think get that somehow.
Okay, go ahead.
My question deals also with communication. I read that recently the attempt to find the wreck of the Endurance failed because the robot, after nearly terminating its mission, disappeared and they lost contact. And I guess all the data that it had collected was lost with it. When your robots surface, do they send off the data they have accumulated, or do you wait until you've got
No, so we send a portion of the data every time just for that reason. So the data I showed you from Hurricane Irene, that glider died. The storm killed it. But we got enough data to essentially help the Weather Service transition how they're going to do their weather forecasting. And so you're often sort of doing the trade-off of if it's a real important data set, you can afford to spend the time at the surface to download it. If it's just doing a standard mission, it's doing it. And the data comes out and it goes several places simultaneously. It goes to our lab, it gets plotted to the web, and is posted within minutes. It goes directly to the Global Weather Service, all the temperature and salinity data, so it can go right into all the forecast models to help with forecasting. And if you're doing applied missions, it goes to your other users.
I have a salinity question. Well, you guys maybe you get the from here, Sophia. Thank you. I study this very salty place, and the South Arm of the lake is around 15% of the size, and the North Arm is about 34%. And I'm always telling students that the ocean, for comparison, is about 3.4%. Is that true everywhere? And where Arctic ice is melting, are you seeing a dilution event where you're seeing less saline water? And are we going to expect that impact to go further than that localized area?
We do see the dilution effect right near the ice shelves, especially near the glaciers. It's tiny. It's by 0.001%, but you can see it. So you can see where the plumes are.
Is it freshwater lensing, like on top of
Yeah,
the
it's just a freshwater lens. And sort of why we think the plants grow well down there is you get a freshwater lens. It's right by ice. The ice protected the plants attached underneath from the wind in the winter. And those two things combined is what kickstarts plant growth. So your lake is an extreme environment. I can't even imagine.
I'm pretty happy about that. Okay, so who has, you have the microphone.
Two-part question. One is, do you work with the military at all on any of this? And the second piece of it, you're throwing around some big numbers. How do you get the funding for all of this?
So the big number part is we write a lot of grants. We're pretty diversified for our funding. So we have federal agencies, we have foundations, and we have companies. So the robotic groups, they pay for my graduate students. My technician time is paid for by companies. The offshore wind area is going to do it. And the reason that they're paying for it is they save money. So the Board of Public Utilities for New Jersey has a big issue in the summertime. So some days you'll get a sea breeze coming onto the ocean, onto the coast, in the coastal communities. No one turns on their air conditioner. On the days there's no sea breeze, everyone turns on their air conditioner. And you're talking in that hub of the country, almost 20% of the U.S. population. So the Board of Public Utilities has to buy enough power to guarantee that it doesn't have a brownout. But if they buy too much, they get charged a pollution tax. And if they buy the day of, it's like buying a plane ticket. It's 10 times more expensive. So we run models of the atmosphere and ocean, and essentially they pay us to do it. Scientists are cheap. Look, we'll pay for a technician and we'll buy you a computer. We're like, oh my God, that's awesome. And we give them a probability chart of the probability of a sea breeze, and they save millions on a hot summer weekend. So it's a lot of money. Our group is pretty big with graduate students and technicians. There's 5 faculty. We built it together. We share it among all our projects. But there's about 30 technicians and graduate students in the group. So we raise about $2 to 5 million a year. And so it's a lot of grant money. Military, absolutely. The oldest science agency in the United States is the Navy. It decided after the War of 1812, when it landed the Marines at high tide, it would never be left behind in basic science. And they're the ones that let you do crazy things. So if I go to a formal agency, I write a big book, they read it, and they go, well, we didn't like your typo on page 62. No. Navy, send us 2 pages of your craziest ideas. So they're the ones who developed all the gliders, all these ocean networks, and they can translate it now into the Weather Service, NOAA, this and that. We have done applied missions. We were in the LOC early on to demonstrate the capability, and that led the Navy now to buy 250 of these gliders, and we're the trainers for them. The funny story of the Asia mission, we can never plot it, but we were up there with a bunch of gliders. A big typhoon was blowing in. They wanted to get all the gliders recovered, so there was no evidence they'd been there. And it was getting bad, and they called us up at 3 a.m. in the morning our time, said, we're making one more pass. If we don't get it, we're going to blow it up. That's sort of a sobering way to wake up in the middle of the night. That didn't happen. The engineer of the ship also had worked rodeo. This is a true story. And he lassoed the tail on the final pass. So that's how it is. Pretty much if you look at ocean work, it's super expensive. It's just the nature of that kind of business. It used to be heavily funded by the Cold War, because the Cold War was really about subs. And because that was the one asset that no one pursued. So our lab actually started in trying to forecast the Gulf Stream and the rings to figure out where the Russian subs were off the eastern seaboard. And so what tends to happen is you have agencies like that invent the crazy stuff, and then it translates it. NASA's another one that invests in the crazy stuff, and then it translates into day-to-day to science.
Awesome. Okay, we have time for one more question. Right in the middle.
This seems like a perfect technology looking for point sources of any kind of pollution, chemical, thermal, whatever. Have you thought about ways that they might be utilized for that purpose, and are there any plans?
So
Yeah.
to
Not
point
necessarily
sources.
just in the ocean.
Yeah, no, actually to go back to the other question, is the military involved? We've actually done it. For that kind of a question, a point source, you generally use the propeller robots because they're fast and they're very precise in location. So there was an experiment on the west coast of the U.S. looking for explosive ordnances, and they had a barrel they put under the water, they hit it and poked holes in it, and then essentially built a nose, essentially a mass spectrometer the size of a Coke can that fits in it, and released it a few miles away and told it to find it. And it took a few hours. It found actually the barrel, and the great thing is there was a bunch of photographers trying to document the moment, and the robot was so focused on the barrel it almost took out one of the barrels. The problem now is more developing robust sensors for the specific kind of pollution. So for plastics, you either collect a piece of plastic or you collect sort of what's dissolving off it. The chemistry is just to the point where we can do it in little handheld devices and dip it in the water by 3 labs. And so now it's being translated into something to be robust. So if it's a sensor this big, you can do it pretty quickly, you know. And so it's up to local sort of water authorities, state agencies, universities. Universities usually get the state agencies interested because they save money. You know, the state of New Jersey used to be collecting, 20 data points. We give them about 25 million data points a year. And so that's the future.
Awesome. I'd like to end on that note about the future, and I appreciate all of the work that you've talked about in the oceans and also getting us excited about science. Thank you so much.
Thank you.